Torque. Torque. Torque is defined as the cross product of position vector and force vector. Suppose if we imagine OX, OY are the axes in a horizontal plane and OZ is vertical. From O, if a string is tied to a stone, suppose the circle in the figure represents a stone and it is tied to a pole along OZ by a rope, by a string, and the length of the string is R, then the position vector is from O to the point where the force is applied, that is up to the circle, center of the circle. This is the radius vector, position vector R bar. And the direction of force is shown in the figure. F indicates the arrow near F indicates the direction of the force. Then the angle between the position vector and force vector is indicated by theta on the right side, indicated by theta to the right of circle. Since the vertical opposite angles are equal, the left side angle will also become equal to theta. Now, in the vector form, the torque is given by tau bar is equal to R bar cross F bar. R bar and F bar are in the plane, in the horizontal plane, indicated by OX, OY, and tau bar is perpendicular, that is along OZ, perpendicular to the plane contained by R and F. The magnitude of this torque is given by F into R sin theta. The magnitude is given by F into R sin theta. This can also be interpreted as the force multiplied by the perpendicular distance from the axis of rotation. If we consider the length of the radius vector as R, then the perpendicular ON becomes equal to R sin theta. The perpendicular ON becomes equal to R sin theta. Hence, the moment of the force is F into R sin theta, force multiplied by perpendicular distance. This is the magnitude of the torque. The torque is 0 if theta is 0 or 180. The torque is 0 if theta is 0 or 180. The unit of torque is Newton meter. The unit of torque is Newton meter. Torque is defined as the turning effect of a force. It is defined as the turning effect of a force. In vector form, it is given by tau bar is equal to R bar cross F bar. It is an axial vector or pseudo vector. It is an axial vector or a pseudo vector. Its magnitude is given by force multiplied by perpendicular distance from axis of rotation, that is F into ON. Sign convention. Sign convention. To understand this sign convention, let us take the figure. Imagine it to be a rod and at O it is supported on a wedge. And two forces P and Q are applied at A and B on this rod. Then, due to P, the rod rotates in the anti-clockwise direction. Due to Q, it rotates in the clockwise direction. Now, due to these two forces, P and Q, two torques are produced. The torque due to the force P is P into OA. This is magnitude. This is magnitude. The direction of this torque will be out of the screen. Out of the screen. That is shown by downward arrow. We have to imagine it to be perpendicular to the rod and out of the screen. It is indicated by a dot in a circle. This is the symbol used for the direction of torque out of the screen. So, whenever the rotation is in the anti-clockwise direction, then the torque will be situated out of the plane. The direction of the torque will be perpendicular to the plane and out of the plane, and it is indicated by a dot in a circle. If you consider the force Q, this force Q rotates the rod in the clockwise direction. In the clockwise direction, the magnitude of the torque created by Q is Q into OB. Q into OB. This torque is situated into the screen. This torque is situated into the screen. It is denoted by dotted arrow above the horizontal line. Above the rod, it is given by a dotted arrow. Above that arrow, an into mark inside a circle is shown. It represents the torque is into the screen and perpendicular to the screen. Into the screen and perpendicular to the screen. So we have to imagine that arrow perpendicular to the screen and into the screen. So this is the direction of clockwise torque. Like this, anti-clockwise torque is taken as positive and clockwise torque is taken as negative. Anti-clockwise torque is taken as positive. So clockwise torque is taken as negative. Couple two equal and unlike parallel forces acting on a body at different points constitute a couple. Let us suppose AB is a rod and F are the forces acting at A and B. They are of equal magnitude and opposite in direction. Then these two forces together constitute couple. They are acting at different points, they are parallel, their magnitudes are equal. Then the torque created by the couple. The torque created by the couple will be the force at A creates a torque F into OA. The force at B creates a torque F into OB. Hence, the total torque by the couple is tau is equal to F into OA plus OB. F into OA plus OB. So, tau is equal to F into AB. This is the total torque. From the figure, this creates the torque creates clockwise rotation. Clockwise rotation. A couple produces pure rotation. A couple produces pure rotation. For example, water sprinkler. In lawns, we use water sprinklers. Opening and closing of the tap. Winding the spring of a clock. So these motions are due to couples. Due to couple. Definition of couple. Two equal, unlike, non-collinear parallel forces constitute a couple. Two equal, unlike, non-collinear parallel forces constitute a couple. So the forces acting must be of equal magnitude and they should be parallel in opposite direction and they should not be collinear. Such pair of forces known as couple. Energy of a rotating body. Suppose a body is rotating about an axis y prime. Consider the particles of this body m1, m2, m3. Three particles of mass m1, m2, m3. Their perpendicular distances from axis of rotation are say r1, r2, r3. If the body is rotated such that the radius vectors have a constant angular velocity omega, if the body is rotated with constant angular velocity omega, then the linear speed of the particle m1 is r1 omega, the linear speed of m2 is r2 omega, the speed of m3 is r3 omega. The speeds of the particles m1, m2, m3 are r1 omega, r2 omega, r3 omega. v1 is r1 omega, v2 is r2 omega, v3 is r3 omega. So, the kinetic energy of the particles m1, m2, m3 are half m1 v1 square, half m2 v2 square, half m3 v3 square, etc. So, if we want to calculate the total kinetic energy of the body, we have to consider the sum of the kinetic energies of all the particles of the body. All the particles of the body. So, it is written in the form of Ek is equal to half m1 v1 square plus half m2 v2 square plus half m3 v3 square plus so on. Like this, by adding the kinetic energy of all the particles of the body, we will get the total kinetic energy of the body. The total kinetic energy of the body is half m1 v1 square plus half m2 v2 square plus half m3 v3 square plus so on. By substituting the values of v1, v2, v3, we will get the total kinetic energy as half m1 r1 square omega square, half m1 r1 square omega square plus half m2 r2 square omega square plus half m3 r3 square omega square plus so on. The total kinetic energy is half m1 r1 square omega square plus half m2 r2 square omega square plus half m3 r3 square omega square plus dash dash dash. In these terms, half and omega square are common. Hence, Ek can be written as half into m1 r1 square plus m2 r2 square plus m3 r3 square plus dash 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 multiplied by omega square. By taking half and omega square as common, the remaining terms are m1 r1 square plus m2 r2 square plus m3 r3 square plus dash dash dash. So Ek becomes equal to half into m1 r1 square plus m2 r2 square plus m3 r2 square plus so on multiplied by omega square. Here the term inside the brackets m1 r1 square plus m2 r2 square plus m3 r3 square plus dash dash dash. This is indicated by the letter I, capital I, known as moment of inertia. So m1 r1 square plus m2 r2 square plus m3 r2 square plus dash 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 is indicated by the letter I, and it is known as moment of inertia of the body. Moment of inertia of the body. Hence, the kinetic energy becomes equal to half I omega square. The relation for kinetic energy reduces to the form Ek is equal to half I omega square. Properties of moment of inertia. Moment of inertia depends on distribution of mass. Moment of inertia depends on distribution of mass, axis of rotation. It depends on distribution of mass and axis of rotation. It is analogous to mass. Moment of inertia is similar to mass. It opposes torque. Mass opposes force. Similarly, moment of inertia opposes torque. The role played by mass in linear motion. The role played by mass in linear motion is played by moment of inertia in rotatory motion. Mass is linear inertia. Moment of inertia is rotational inertia. It is sum of mr square. Sum of mr square terms, that is the mass of particle multiplied by the square of the distance from axis of rotation. Sum of such terms gives the moment of inertia. Radius of gyration. Radius of gyration is a distance from axis of rotation. It is indicated by k. Radius of gyration is the distance from axis of rotation indicated by k. And this distance is such that mk square gives the moment of inertia of the body, where m is the total mass of the body. If m is the total mass of the body and mk square gives the moment of inertia of the body, such a distance k is called the radius of gyration of that body. The radius gyration of that body. Let us suppose a body is composed of several particles of equal mass. A body is composed of several particles of equal mass. Then m1 is equal to m2 is equal to m3 is equal to dash 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 is equal to m. From the relation I is equal to m1 r1 square plus m2 r2 square plus m3 r3 square plus dash 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 plus mn rn square, by using m1 is equal to m2 is equal to m3 is equal to dash dash is equal to m, we will get I is equal to m into r1 square plus r2 square plus r3 square plus dash 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 plus rn square. I is equal to m into r1 square plus r2 square plus r3 square plus dash 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 plus rn square. The total mass of the body becomes equal to capital M is equal to small m into n. Small m into n gives the total mass of the body. By imagining the particles are of same mass and using the relation for moment of inertia I is equal to m1 rn square plus m2 r2 square plus m3 r3 square so on, I is equal to m into r1 square plus r2 square plus r3 square plus dash 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 plus rn square. Let us multiply the numerator and denominator with n. Then we get the relation for I as mn into r1 square plus r2 square plus dash 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 plus rn square by n. I is equal to mn into r1 square plus r2 square plus dash 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 plus rn square by n. This is the relation we get for I by multiplying numerator and denominator with n. Now mn becomes equal to capital M, the total mass of the body. I is equal to mn into r1 square plus r2 square plus so on plus rn square by n. In this relation mn is capital M. So I is equal to capital M into R1 square plus R2 square plus dash dash Rn square by n. Let us substitute R1 square plus R2 square plus dash 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 plus Rn square by n as k square. Then we will get the relation for I is equal to mk square. I is equal to mk square, where k square is R1 square plus R2 square plus dash 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 plus Rn square by n. So k becomes equal to square root of R1 square plus R2 square plus dash 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 plus Rn square whole divided by n. K is equal to square root of R1 square plus R2 square plus dash 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 plus Rn square whole divided by n. K is square root of R1 square plus R2 square plus dash 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 plus Rn square by n. To understand the radius of gyration, distance radius of gyration, let us see the figure. In the figure, small m1, m2, m3, etc. They are all the masses of the particles, and capital M is the total mass of the body. So the distances of small m1, m2, m3 are r1, r2, r3, and the distance of capital M is k. So this is the distance radius of gyration. It is a perpendicular distance from axis of rotation where the entire mass of the body appears to be concentrated. Supposed to be concentrated. We treat the entire mass of the body as though it is concentrated at this point, and this distance, perpendicular distance from axis of rotation, is taken as radius of gyration, and it is equal to the root mean square of the distances of the masses, particles. Root mean square of the distances of the particles of the body. It is mathematically k is square root of r1 square plus r2 square plus dash dash Rn square by n.